Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 17, Symmetry and Conservation, what the universe refuses to change. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are walking deeper into the heart of Book 9.4, Dynamical Grammar, in Episode 9. Our journey here has built a formidable structure. We discovered the director, the actions phi, a cost function that selects which stories the universe tells by preferring those of least action. We then learned the director's method, the equation derivation rules, the calculus of variations, that translate the global command minimize cost into local equations of motion, the Euler-Lagrange equations. We now have a machine. Input an action, turn the crank of variation, output the laws of dynamics. But as we watch this machine run, a breathtaking pattern emerges, a pattern so profound it feels like uncovering the universe's deepest secret. We notice that certain numbers in perfectly isolated systems never change. The total energy of a swinging pendulum, ignoring friction, remains constant. The total momentum of two colliding balls remains the same before and after. The total angular momentum of a spinning ice skater pulling in her arms is conserved. These are not accidents or separate laws. They are inevitable shadows cast by the very structure of the action itself. Today, in Part 17, Symmetry and Conservation, we discover the sublime link between what remains unchanged in the grammar and what remains unchanged in the story. We will learn Noether's theorem, named for the mathematician Noether, which states, in essence, for every continuous symmetry of the action, there is a corresponding conserved quantity. This is the moment when the holophase language reveals its own stubbornness, its own inviolable rules of permanence amidst endless change. Our anchor image for this climb is a perfectly balanced, rotating mobile hanging in a still room. The mobile is an intricate sculpture of shapes and rods. It turns slowly, its pieces moving in a complex dance. But watch carefully. No matter how the pieces move relative to each other, the center of mass of the entire mobile hangs perfectly still, directly below the suspension point. This is a conserved property. The weighted average position doesn't budge. Why? Because the mobile's construction and the force of gravity possess a symmetry. The physical laws governing it are the same in every horizontal direction, rotationally symmetric around the vertical axis. This symmetry of the rules forces a conservation law, conservation of the horizontal position of the center of mass. If you try to push the center of mass sideways, the mobile will react to restore it. The universe is this mobile on a cosmic scale, and its symmetries are written into the action side. Here is the beautiful, powerful puzzle of this part. We have derived equations of motion from the action. These equations describe change, how phi evolves. Yet, solutions to these equations often exhibit quantities that do not change. They are conserved. Where does this permanence come from? How can a principle about change, least action, give rise to laws of non-change, conservation? The answer lies in the concept of symmetry. A symmetry is a transformation that leaves something looking the same. In the holophase language, We are concerned with transformations that leave the actions phi unchanged. Think of the action as a recipe for the cost of a story. A symmetry is like changing how you read the recipe, shifting the time you start cooking, moving the kitchen to another city, rotating the oven, in a way that doesn't alter the total cost of the meal. If the cost is insensitive to such a shift, the recipe has a symmetry. Noether's genius was to prove a theorem that connects this indifference of the recipe to a guaranteed permanence in the meal. The theorem, translated for our ears, says, if you can change phi in a continuous, smooth way, a symmetry transformation, and the action S does not change at all, then there exists a specific quantity constructed from phi and its derivatives that remains constant in time for any story that obeys the equations of motion. Let's make this concrete with the three foundational symmetries of nature. Time translation symmetry, conservation of energy. Imagine shifting the entire story of phi, every event, to start a little later or end a little later. If the action S does not depend on when the story happens, if the laws of physics are the same yesterday, today, and tomorrow, then S is symmetric under time translation. Noether's theorem then guarantees there is a conserved quantity. That quantity is energy. In our Holophase terms, energy is a specific tally built from phi and its time derivative omega, which remains constant as phi evolves. The time echo of symmetry is persistence. Space translation symmetry, conservation of momentum. Now imagine shifting the entire story of phi, every value, a little to the left, right, up, or down in space. If the action S does not depend on where in space the story happens, if the laws of physics are the same here as over there, then S is symmetric under space translation. Noether's theorem then guarantees a conserved quantity, momentum. Momentum is a tally built from phi and its spatial gradient k. The space echo of symmetry is uniformity of law. Rotation symmetry, conservation of angular momentum. Imagine rotating the entire story of phi in space. If the action S does not depend on the orientation, if the laws of physics are the same in all directions, then S is symmetric under rotation. Noether's theorem gives us angular momentum, a tally involving both position and momentum, or, for fields, involving k and spatial position. The motion echo of symmetry is the preservation of spin and orbital motion. So here is the point, a cornerstone of all physics. The great conservation laws are not separate commandments. They are direct, inevitable consequences of the symmetries woven into the fabric of the action, into the universe's narrative cost function. Energy is conserved because the laws of physics don't have a favorite moment in time. Momentum is conserved because they don't have a favorite location in space. The stubbornness of these conserved numbers mirrors the indifference of the grammar to when and where the story is set. Let's explore the tri-unity of this deep connection. The time echo of symmetry, the eternal ledger. Time translation symmetry means the cost accounting rule, the action, is the same for any time interval you choose. This temporal uniformity forces the existence of a time-like constant, energy. Energy is the currency that can be converted between forms, kinetic, potential, thermal. But in a closed system, the total balance never changes. The time echo is this permanent accounting. It's why perpetual motion machines of the first kind are impossible. You cannot create energy from nothing because the grammar's indifference to when you start forbids it. The ledger's total is fixed from the beginning of time to the end. The space echo of symmetry, the homogeneous canvas. Space translation symmetry means the cost rule is the same at every point. This spatial uniformity forces the existence of a space-like constant, momentum. Momentum is the oomph of motion, and its conservation means the total oomph of an isolated system cannot change. It can be transferred from one object to another in a collision, but never created or destroyed. The space echo is this homogeneity of impulse. It's why a rocket works in empty space. It throws exhaust backward, gaining forward momentum, and the total, rocket plus exhaust, momentum remains zero. The motion echo of symmetry, the choreography of rotation. Rotation symmetry means the cost rule is the same in every direction. This isotropy forces the existence of an orientational constant, angular momentum. This governs spinning tops, planetary orbits, and the formation of galaxies. The motion echo is this preserved swirl. It's why an ice skater spins faster when she pulls her arms in. Her angular momentum must stay constant, so reducing her rotational inertia demands an increase in rotational speed. The symmetry of the stage dictates the conservation of the dance's spin. Now, let's locate this magnificent theorem on the master tree. We are on the symmetry conservation branch, a soaring limb growing directly from the equation derivation node on the dynamical grammar trunk. This branch depends critically on the Euler-Lagrange equations. Noether's proof uses them to construct the conserved current. It enables the next profound step, the understanding of gauge symmetries and force interactions, where more abstract symmetries, like phase rotation of a complex field, lead to conservation of electric charge and the very existence of gauge fields, like the electromagnetic field. It also provides the ultimate rationale for using conserved quantities to solve problems. They are the immutable landmarks in the flowing landscape of change. To ground this supreme abstraction, let's light lanterns from across all scales of understanding. A near lantern from board games and sports, the conservation of pieces or score. In a game of chess, the total number of pieces is not conserved, they are captured. But some games have strict conservation. In a game of pool, before the break, the total momentum of all balls is zero. After the break, the cue ball transfers momentum to the others, but the vector sum of all momenta remains zero. Some balls go left, others right, canceling out. This is a direct manifestation of spatial translation symmetry. The pool table laws are the same everywhere on the felt. If you secretly had a magnetic table that pulled balls north, that symmetry would be broken and momentum would not be conserved. Balls might all drift north over time. The conservation rule is a fingerprint of the symmetry of the game's action. A middle lantern from planetary astronomy, the stability of orbits. A planet orbiting a star has a conserved angular momentum, neglecting other planets and tidal forces. This is due to the rotational symmetry of the star's gravitational field. It pulls equally in all directions around it. This conservation forces the orbit to lie in a plane and gives us Kepler's second law. The planet sweeps out equal areas in equal times. When we send a satellite to another planet, engineers perform gravity assists, using a planet's motion to change the satellite's momentum and energy. Crucially, during this maneuver, the total energy and momentum of the satellite plus planet system are conserved. The satellite gains energy by stealing a tiny, imperceptible amount from the planet's orbital motion. The symmetry-derived conservation laws allow for precise, reliable calculations across the solar system. A far lantern from particle physics. The conservation of baryon number and lepton number. In the subatomic realm, we observe that the number of baryons, like protons and neutrons, minus antibaryons, is conserved in all known interactions. Similarly for leptons, electrons, neutrinos. These are not yet fully explained by a known gauge symmetry like electric charge, but they are treated as empirical conservation laws that strongly hint at deeper symmetries in the action at a fundamental level. The search for a unified theory is, in part, a search for the symmetry principle that yields these conservations. When we observe rare processes like proton decay, which would violate baryon number, it would be a direct signal of a symmetry broken at some high energy scale, a monumental discovery. Here, conservation is the experimental guidepost pointing toward hidden grammatical structure. From the pool table to interplanetary travel to the stability of matter itself, the theme resonates. Invariance in the rules, symmetry, begets invariance in the play, conservation. The things that never change in the drama reveal what the playwright considered irrelevant to the story's cost. What then is the specific language role of Noether's theorem? It is the grammatical meta-rule of correspondence. It is the syntactic rule that maps a property of the declarative statement, the action is symmetric under transformation X, to a property of the imperative output, the equations of motion imply a conserved current Y. It is the bridge between the adjective of the grammar and the noun of the story. It answers, what permanent feature of the narrative is guaranteed by this indifference in the narrative cost rules? The core question this part asks about phi is, what continuous transformations leave the action as phi invariant, and what corresponding conserved quantities, currents, charges, does this invariance dictate must exist for any solution of the equations of motion? We are moving from analyzing the dynamics of change to identifying the immutable signatures within that change. What does this symmetry conservation link do in the generative process? It explains the existence and origin of the great conservation laws, unifying them. It provides powerful solution methods for equations. Conserved quantities are constants of motion that reduce complexity. It guides the construction of new theories. Demanding a symmetry, like local gauge symmetry, forces the introduction of new fields, like the photon field, to maintain it. It offers a profound classification of forces and interactions based on the symmetries they respect or break. Now, stability and breakdown. The connection between continuous symmetries and conservation laws is a mathematical theorem within the framework of Lagrangian Hamiltonian mechanics. It is rigorous and exact. It breaks down in two important ways. One, discrete symmetries, like mirror reflection, do not generate conserved currents via Noether's theorem, though they are important. Two, explicit symmetry breaking. If the action S itself is not symmetric, if we put terms in it that pick a preferred time, location, or direction, then the corresponding conservation law is broken. Energy is not conserved in an expanding universe, cosmological time dependence. Momentum is not conserved on a surface with friction, the surface breaks translational symmetry. Angular momentum is not conserved in a system with an external torque. The theorem tells us precisely what we lose when we break a symmetry. This brings us to the rigorous core of our discipline: falsifiability. The claim that conservation laws arise from symmetries of the action is a profound structural prediction of the Holophase grammar, open to dramatic test. The central claim: for any isolated physical system described by a holophase action as phi with a specific continuous symmetry, the corresponding quantity, energy, momentum, charge, will be conserved in precise experiments. If we can engineer a situation that breaks that symmetry in the system's effective action, we should observe a controlled violation or modification of the conservation law, predictable from the broken symmetry. A concrete measurement scene, testing conservation of linear momentum in a low-friction environment. We set up a nearly ideal one-dimensional air track, a long, straight rail with tiny air holes that levitate gliders, minimizing friction. We have two gliders with known masses, equipped with spring bumpers for elastic collisions and Velcro for inelastic collisions. We also have a means to apply a small, constant external magnetic force to one glider, breaking translational symmetry. We use high-precision motion sensors to track the glider's velocities before and after events. Experiment 1. Isolated system. We propel one glider into another at rest. We measure total momentum, mass times velocity for each, summed, before and after the collision for both elastic and inelastic cases. Experiment 2. Broken symmetry. We turn on a uniform magnetic field that applies a known constant force to one of the gliders, say the rightward one. We repeat the collision experiments and measure total momentum before and after, now in the presence of this external force. The pass condition. In experiment 1, isolated symmetric system, the total momentum before and after collision is equal within the very small experimental error, accounting for minimal air resistance and sensor noise. The data confirms conservation. In experiment 2, broken symmetry by external force, the total momentum is not conserved. The change in total momentum between before and after the collision is measured, and is found to equal the impulse delivered by the external force during the collision time interval, force times delta t. This is exactly predicted. Breaking space translation symmetry via an external force introduces a source sink of momentum. The failure of conservation is quantified and matches the prediction derived from the modified equations of motion, which now include the external force term breaking the symmetry. The fail condition. Falsification. In experiment 1, under ideal, isolated conditions, total momentum systematically drifts. It is not conserved even after accounting for all known measurable losses. Or, in experiment 2, the measured change in momentum does not match the calculated impulse from the external force. Even more damaging, if we discover a fundamental process in an apparently isolated system, like a radioactive decay in free space, where momentum is not conserved, say an electron is emitted in one direction without a recoiling nucleus in the opposite direction, it would falsify the idea that momentum conservation stems from a fundamental symmetry of space-time. It would mean our deepest action for particle physics lacks that symmetry, a revolutionary finding. This falsifiability ensures that the beautiful, almost philosophical link between symmetry and conservation remains rooted in hard, measurable physics. Let's cultivate a practical recognition skill. You can train your intuition to see the symmetry conservation link in any system where a rule or environment is uniform in some aspect, leading to something that is persistently counted or balanced. Observe a closed ecosystem in a terrarium. The total amount of water is approximately conserved. Why? Because the glass walls are impermeable to water molecules. They enforce a symmetry. Water molecules inside are treated identically. None are allowed to cross the boundary. The rule, the boundary condition, is symmetric with respect to the identity of water molecules inside versus outside, leading to conservation of their number inside. If you poked a hole, breaking that symmetry, water would not be conserved in the terrarium. Consider a fair, sealed auction. The total amount of money in the room is conserved. It just moves from bidders to the auctioneer. This conservation arises from the symmetry or rule that no money is printed or destroyed during the auction. The economic action, the rules of exchange, is symmetric under the reassignment of dollars between people, leading to conservation of total cash. Watch a kaleidoscope. As you rotate it, the beautiful symmetric pattern changes, but the number of reflected image segments is conserved. This conservation arises from the fixed symmetry, the angular arrangement of mirrors, of the device itself. The optical laws inside the kaleidoscope have a discrete rotational symmetry, leading to a conserved quantity, the number of copies. Whenever you notice that the system has a property that doesn't change despite internal rearrangement, look for uniformity or invariance in the rules governing the system. You are likely seeing a Noether-like principle in action. We must connect this supreme insight deeply to our Holophase journey. In the previous part, we learned to derive equations of motion from the action. Here, we've learned that the very symmetries that allow us to derive those equations also implant into them seeds of permanence, the conservation laws. The grammar is not just generative and selective, it is also protective. It builds into its stories certain unbreakable rules, certain quantities that must be passed unchanged from sentence to sentence, chapter to chapter. This is how the universe maintains coherence across time and space. If you want to see the full mathematical derivations and exact equations behind this idea, the precise formulation of Noether's theorem, the construction of the conserved current J mu, the derivation of the continuity equation partial mu J mu equal to 0, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and absorb the majesty of our position in Book 9.4. We began with the action as selector. We derived the equations of motion as its local voice. And now we have discovered that the symmetries of the action whisper the eternal truths of conservation. We have the complete logical chain. Symmetry of S, stationarity of S, action principle. Equations of motion, conserved quantities. This is the core of classical field theory and the foundation for quantum field theory. In the next part, we will add the final vibrant layer to dynamical grammar, nonlinear interaction rules. We have so far dealt mostly with linear systems, where waves pass through each other. But what happens when the action includes terms where phi interacts with itself? Terms like phi cubed or phi to the fourth. This is where waves stop being independent sentences and start having conversations. They scatter, they create new waves, they exhibit chaos and solitons. This is the grammar of complexity, the rules by which the simple holophase field weaves the intricate, interactive tapestry of the world we see. Before we end, the mandatory zoom out to hold our scope. The conserved quantities, energy, momentum, angular momentum, charge, are not new substances. They are specific, derived tallies built from phi and its derivatives, whose constancy is guaranteed by the symmetries of the action S, which is itself built from phi and its derivatives. We have added no new metaphysical layers. We have simply traced the logical consequences of the grammatical structure we've been assembling. One field, phi, plus its infinite tower of derivative questions, plus the principle of stationary action, plus the symmetries of that action. From this, the great pillars of permanence arise. The universe refuses to change what its own grammar deems irrelevant. As we conclude, hold the image of the perfectly balanced mobile. Its complex, moving parts are like the changing configurations of the phi field. The unmoving center of mass is the conserved quantity. The invisible rods and strings, the symmetry of the construction, are the action S. Noether's theorem is the understanding that the stillness of the center is guaranteed by the perfection of the symmetry. The universe is this mobile, hanging in the void. Its stories swirl and collide. Stars are born and die. Particles annihilate and are created. But through it all, certain sums of energy, of momentum, of charge remain fixed, silent sentinels of the grammatical symmetries written into the first sentence of phi. The universe is a story of endless change, built upon a foundation of sacred, unchanging numbers. Salam, and peace be upon you.